Hey, hello. My name is Kamwoo Lee. I'm a data scientist at the World Bank. I'm going to present my work on high-resolution poverty maps in sub-Saharan Africa. And I put the resulting map on the right side of the slide, so you can take a look at it along the way. So this research paper was published in November 2022, so it's a bit outdated, but I hope you can get any insight for your work. So the goal of this project is quite simple. It is to estimate current welfare status of all populated places in sub-Saharan Africa on the village level. I mean, 1 million populated places in a 1 square mile area. If you look at the map on the right side, each dot is a 1 square mile inhabited places. So the redder the poor, the bluer the richer. So how can I do that? I used publicly available data sources and a couple of machine learning methods on top of previous researchers' great ideas. So over the past few years, there have been major advances in estimating socioeconomic indicators with machine learning and geospatial information. Machine learning, as you may know, is an application of AI that makes computers to automatically learn and improve from examples. So basically, we throw examples of geospatial data and wealth level to a computer and tell it, hey, computer, you figure out the relationship between the geospatial information and wealth index from the examples and bring me a prediction model. That's what I did. There are generally two categories of machine learning methods to do this kind of estimation. One is what I call feature-based prediction model, which uses pre-quantified indicators, variables, at least for humans, and human understandable criteria of geospatial features like number of buildings, area of buildings, length of road, number of junctions, etc., etc. And then we train a model and we can estimate all other places. The second category is image-based prediction model. So image-based model uses satellite images or aerial pictures to capture non-quantifiable geospatial characteristics. So through the training, this type of model learns image characteristics and how they are related to wealth level. Very often, these image characteristics are hard to interpret. It can be densities of specific colors and distribution of shades and how rectangular objects on the pictures are, or how an object can be decomposed with segments of lines. But to computer's eyes, they are very, very clear predictors for wealth levels. And these are publicly available data sets that I could find at this project. I used DHS wealth index as a predicted variable, and I used I extracted the number of buildings, area of buildings, length of roads, number of junctions, etc., from OpenStreetMap data. I also used nighttime luminosity. So I extracted max, median, average, zero, upper third, lower third, the nighttime luminosity. I also used population density, and of course, daytime satellite images. I used only publicly available data sets just because I want others to replicate the result. So we have data and we have methods, but we have two problems to solve. First, many countries don't have survey data to train this kind of model in the first place. Think about South Sudan and Somalia. We have absolutely no survey or census data to begin with. The second problem is that feature-based model and image-based model they are fundamentally different. So previous researchers used them separately. So the problem number one is about the limitation of training data. As you know, DHS wealth index is a survey-specific measure, so you cannot take other countries or other surveys index and apply to our country of interest. And problem number two is a limitation of method. So feature-based model cannot capture any non-quantifiable differences. So let's think about a road. I mean, mountain trail is very, very different from a highway, even though the length are the same. Of course, you can incorporate all the possible characteristics of a road, but they are fundamentally human-generated features. And the problem about image-based model is that they cannot capture out-of-image information. Of course, distance to closest hospital, closest school, market, even though they are very important information to estimate wealth. At the same time, image-based model requires a lot more training data, but very often we don't have enough training data. And previous researchers resort to use a nighttime luminosity as a proxy to wealth level, but it's a fundamentally limited. Think about look at the right bottom picture. It's a Cameroon. It's the mean nighttime luminosity within 1 square mile. 90% of the nighttime luminosity is 0. 90% 0, so it's not a very good proxy, I think. So my solution is to create cross-country estimation model. So we take examples from other country and apply the model to the country of my interest. And I also suggested a self-refining mechanism using both feature-based and image-based model. Solution number one. So there have been some attempts to make DHS wealth index comparable, like CWI, HWI, IWI. I chose IWI because we can apply to large number of countries at a fixed time frame. It's a strictly comparable asset-based index that can be applied to all middle and low-income countries. Solution number two is the highlight of this research work. It's training data, self-refining mechanism. I first trained the feature-based model with OpenStreetMap data, nighttime light, and population density, and estimated wealth index for all populated places. So at this point, this wealth estimation is better than nighttime luminosity. So I used that to train an image-based model. So after training, I use that model to generate estimate wealth index for all populated place. So I have a wealth index trained on non-quantifiable image characteristics. So I channeled it to the feature-based prediction model because I already make it as a feature. So I trained the feature-based model again. I get better result from that. I channeled it again to the image-based model. And I did the process 7 times until it reaches it is stabilized. And some of the, so I measure the progress in R squared, and the most improvement are Malawi and South Africa. So the performance improved over 20% over along the way. So the way I see it, most machine learning applications stop at the first step. By constructing a virtuous cycle, a refining mechanism, we can increase the performance. That's what I'm really proposing with this research. I used some additional trick to narrow down DHS clusters. Let me skip it for now. So that's how I created high resolution poverty maps for sub-Saharan Africa. But we cannot use it without proper validation, because without validation, a machine learning model is just a fancy, sophisticated trash. A computer game at best. So we need thorough validation of prediction model. So think about what I'm trying to do. I want to create a cross-validation model. So here's what I did. We have 25 countries data. I left out one country's data and trained the model with 24 countries data and compare the result with the left out country. I left out Angola, I did the same thing. I left out Zimbabwe, I did the same thing. I did it 25 times. And I tried to find a counterexample that this method would fail. Luckily, it didn't fail. And after 25 repeated experiments, now I feel confident this cross-country estimation model works. And the most exciting and promising thing is that cross-country estimation model is as good as single country estimation, and it's even better for some countries. So let's look at the variables data again. Cross-country estimation works. What that means is that these predictor variables are universal, at least in sub-Saharan Africa, to estimate wealth index across countries. And hey, I you have a couple of questions, and most often questions I get is which variable explains the most variance in wealth index? Actually, the answer is 0. 1 square mile, 0 light percentage, and it accounts for 70% of our wealth level. So I can tell what your second question will be. The zero luminosity ratio alone can explain 70% of variance of wealth. So can we simply use the zero luminosity to predict wealth? The answer is no. That's a trap of single metric. We cannot use a single metric to validate. So take a look at the 1 square mile zero light ratio. The distribution is significantly different. Think about what we are trying to do. We want to make a cross-country estimation model. So we have to look at the worst case scenarios. So in this case, worst case is the R square is 25%. It's almost useless. Total road length, 22%. No. Image-based prediction, no. So we have to look at the distribution and we have to look at the worst case for cross-country estimation model. And I published this map and I released the data through actually Harvard Dataverse, not the World Bank Microdata Library. And I have a few agenda to work later. One of the agenda is slum and segregated area identifying estimation. So if you look at the image, this is just the 1 square mile area. In it, there is both wealth region and very poor region in a single image. So that's what I'm gonna try to do next. Thank you.